Click the bell icon to get latest videos from Ekeeda.
Hello friends, in this particular session we will have to learn the integrator, what that integrator is and how we can implement that integrator with operational amplifier. Let's see. First of all, first question comes in your mind that what is integrator? Integrator, that means I'm integrating input and that I'm feeding up to the output. So simple expression, mathematical expression of the integrator is VO is equal to integrator of input voltage. So this is nothing but your expression for output voltage in the form of input voltage. That expression is of integration. So that is why the circuit is called as integrator. Now question arises how we can implement this integrator. This integrator we can implement by using passive circuit and active circuit, in which active circuit is nothing but of operational amplifier and the passive circuit is nothing but capacitor and resistor. First of all, we will draw a simple integrator and then we will learn what are the limitations of this simple integrator and how to overcome this with practical integrator. We have heard about inverting configuration of operational amplifier. The basic thing. This is nothing but the inverting configuration of operational amplifier. So this will act as an amplifier only, but instead of resistance RF, I have placed the capacitance. So capacitor is playing important role when I am passing the analog input signal, that is Vin, in the form of AC signal. Let us treat this with mathematical sense. If I am considering this as node A and if I apply KCL, so what will be the current flowing through this capacitor? I should know first that what is the current flowing through the capacitor. Current flowing through the capacitor has the value in terms of voltage across capacitor ka derivative. Okay, current flowing through capacitor, that is, let's say IC, which is equal to C into dVc divided by dt. This particular equation we will implement in application of KCL at node A. We will say that this is current IC, but question arises what exactly the value of Vc, that is voltage across capacitor. If we take this plus, this minus, under consideration of the direction of this current, then I will get to know that VA minus VO is nothing but the value VC. VC is nothing but VA minus VO. I know that by using virtual ground concept. This is virtual ground concept where I am getting the value VA is equal to 0. So from virtual ground concept, we will be getting value VA is equal to 0 volts. So your value VC will become VA 0 rakho, you will be getting minus VO. Okay, and then we can easily say that this IC will become C into dVO divided by dt into minus sign. We will take this as equation number 1. And now we will apply KCL at node number A. We will say KCL at node A. Then first of all we will be getting the value of current flowing through the resistance R1, which is in the form of Vin. We will be getting Vin minus VA divided by R1, which is incoming current, and another outgoing current is nothing but current IC. We will just equate this, as I know that as VA is equal to 0, we will say that simply Vin divided by R1 is equal to minus into C into derivative of VO divided by dt. I want VO in the form of V in. So what I have to do? I have to do ulta of that of differentiation, that is nothing but the integration. So we will do integrating both sides with respect to t, that is time parameter, because dt is over here. We will be getting integration of r1, c will come here, minus 1 upon r1 into c into v in dt, which is equal to the value VO. This is nothing but the expression of the simple integrator. This is the expression of the simple integrator. But what are the consequences that we are facing practically in your simple integrator that we have to learn now? We'll again write this expression VO is equal to minus 1 upon R1 into C multiplied by integration of V in into dt. Can we find out the transfer function in the form of frequency domain? We will do convert it into frequency domain. Here I am converting this complete time domain equation into frequency domain. Then I will be getting VO, which is a function of S. Initially it was a function of time, is equal to minus 1 upon R1 into C multiplied by this particular thing. I will say that it's nothing but 1 upon S. If I have integrator, then I will convert this into 1 upon S, that we all have learned in your Laplace transformation, because Laplace transformation is nothing but conversion of time domain into frequency domain, or conversion of one form into another form, one domain into another domain. Then I can say I realize the fact that here 1 upon S into R1C is nothing but your gain factor. So gain which I am getting is looking like this. If you plot graphically, then how the nature is, whether it is practically possible or not. Let us say this is zero frequency and it is increasing logarithmic. This is your gain A, which is nothing but VO of S divided by V in of S in a mod form, so that minus 1 will get rid of. Now as frequency is equal to 0, this whole transfer function will become infinite, and this is not practically possible, and that is why we are facing the consequences here for simple integrator. So as S increases, what will happen? As S increases, the value of gain will decrease. This value will decrease, and this shows that your pole minus 20 dB per decade, because we are having pole at origin. This particular graph is not showing constant value up to particular frequency, and that is why what will happen if frequency is equal to 0. In circuital point of view, you will be getting if C at frequency f is equal to 0. If f is equal to 0, right, at f is equal to 0, your xc is infinite. That means C is equal to open circuit. That means this closed loop configuration will no longer act as closed loop configuration. Rather than that, this will act as open loop configuration, and that is not feasible. That is why we are going for another remedial form of this particular circuit such that this will act as proper integrator with particular value constant gain for particular frequency up to particular frequency, and then it will act as a attenuator. So in all, I want this particular integrator should act as low pass filter with proper cutoff frequency or proper corner frequency, which is decided by the value of the capacitor C and the resistor R which we are placing in this particular circuit. So far we have heard about the two things very important. One is limitations of this particular simple integrator. One is at omega is equal to 0, right? Gain is equal to infinity. And second thing, at omega is equal to 0, circuit acts as open loop configuration, which is not possible to have the integrator. And that is why we are going for another circuit. Let us see what that circuit gives you the idea. For changing the circuit, basically I'm just adding one another parameter in parallel with the capacitor. Here I am adding one resistor into it in parallel with the capacitor. In all, I'm getting this, let's say RF, this is C, this is R, and now here we will be getting V in. This is ROM, has nothing to do with this. So whatever we will be getting, that will be in the form of, let's say, if you take this completely as a Z, then what will be Z? Z is a combination of RF and C, right? So this will give you the gain in the form of Z divided by R. Very simple fact, Z divided by R. Now we will take the gain A is equal to VO of S divided by V in of S. That will come out to be Z divided by R. We will have to first calculate what is the value of Z. What is Z? Z is nothing but RF and C ka parallel combination. So RF multiplied by, in frequency domain we can directly write down RF multiplied by 1 upon SC and 1 upon SC plus RF. This will give you an idea that RF divided by 1 plus RF into SC. We will just implement this particular thing over here such that we will be getting RF divided by R into 1 plus RF into SC. Now if you take this magnitude, then the magnitude of this gain will become VO of S divided by V in of S. That will give you RF upon R in bracket square root of 1 plus RF square S square C square. Now put the value S is equal to 0. Is it possible to get the value which is infinity? No, it is not possible. Rather than that, it will give you open loop configuration ka gain. It will not become infinite value, right? We will be getting the value at omega is equal to 0. That means S is equal to 0. We get the value A is equal to VO of S divided by V in of S at omega is equal to 0 will become RF upon R. So your value will not become infinite, and this is how we can name this circuit as practical integrator, because practically gain is equal to infinite, which is not at all possible. Rather than that, at omega is equal to 0, we are getting RF upon R. That is quite practical, and that is why we can plot this graph as something like this up to certain particular frequency, low frequency, and then we are getting this slope which is of minus 20 dB per decade. Frequency in logarithmic scale and gain. Now one question again comes in your mind that this is some dekha dekha sa graph, right? Just now we can consider this as low pass filter, and that is why we can make a statement, make a conclusion that practical integrator will act as low pass filter. This is very important concept in your objective type of question as well. There are so many questions. Practical integrator will act as low pass filter, band pass filter, and another few options. So you have to tick low pass filter. This is how we have learned the integrator. Now we will draw some waveform, and then we will get to know that how we will be using this particular integrator in your real world with oscilloscope. This is my waveform. Let us say that this is your square wave as input. So I am applying input in the form of square wave time domain, and I'm expecting that what should be my output. So for this particular region, what should be my output? For this particular region, what should be my output? For this particular region, and so on. This is nothing but your step input. So step ka integration is ramp. This is positive value which is going down. As this is positive and we have got gain is equal to -1 upon something. So that minus sign indicates that your slope of ramp will be exactly opposite to this particular value. If this is of positive value, let's say positive VSAT, then your slope will be negative. Okay, so this is how we will be getting the slope. Slope will reach to negative VSAT, negative K into VSAT, and this is plus K into VSAT. We have K purposely because we are getting the constant value of gain even though the initial phase of the signal. This is minus sign, minus VSAT, and when this value is negative, I'm getting positive slope. Mind well. So we will be getting a positive slope over here, and again negative slope over here for positive sign. So I am trying to convert this square wave signal into your triangular wave signal, and this is how we can implement in your regular ICs to convert particular waveform into another type of waveform. So suppose I want to change this waveform from triangular to some another waveform with integrator, then that particular waveform we will be getting in the form of parabolic waveform, sinusoidal waveform. Sinusoidal waveform I can convert into cosinusoidal waveform, and so on. So I can change the nature of the waveform easily by using the integrator. That too depends on which type of nature of input waveform I am using. So this is how we have learned conceptually about simple integrator and practical integrator. In upcoming videos, we will learn the differentiator and practical differentiator. Thank you so much for watching this particular video. If you like this video, then don't forget to like, share and subscribe Ekeeda channel. Thank you so much.